Welcome to UV Physics Academy. So here we are solving the solutions of quantum computation, and this is the next problem. Here they have given one Hermitian operator, okay, and it is having two eigenvectors, let us say psi1 and psi2, corresponding to two distinct eigenvalues, that is a lambda1 and lambda2 eigenvalues, which are distinct. Then we have to show that these eigenvectors are orthogonal. So means two eigenvectors corresponding to a Hermitian operator which is having two distinct eigenvalues are always orthogonal. Okay, let us say, let us suppose A is a Hermitian operator. A is a Hermitian operator. So what is the meaning of this? A is a Hermitian operator means A dagger equal to A, right? Next we have to define two eigenvectors. Let psi1 and psi2 are two eigenvectors corresponding to two eigenvalues, that means let us say lambda1 and lambda2. So with two distinct eigenvalues. So what is the meaning of distinct eigenvalues? Remember, this lambda1 and lambda2 both are not equal. That means non-degenerate, just like that. Okay, so let me write the eigenvalue equation corresponding to A. A operates on psi1. We got lambda1 psi1. This is our first equation. And the second equation, A operates on psi2. We got lambda2 psi2. This is our second equation. Okay, so now I'm taking this first equation and writing in the Dirac notation form. A operates on psi1 equal to lambda1 psi1. You just multiply this equation with the bra vector of psi2. Just multiply with the bra vector of psi2. If you just multiply, then psi2, this is A cap, psi1 equal to lambda1 constant, and here it is psi2 psi1. Just assume this is equation 1. Next, I'm taking this second equation. So before going to multiply, first let me take its Hermitian conjugate. So then if you take the Dirac notation, this is the ket vector and this is the ket vector. If you take the Hermitian conjugate, this is the bra vector psi2 and here it is A dagger, and this is a lambda2 star conjugate and its conjugate is a bra vector. Now I am multiplying with the psi1 on the right side, ket psi1. So multiply with this time a ket psi1. Here I multiplied with the bra psi2 and here I multiplied with the ket psi1. Just multiply psi2 A dagger psi1 equal to lambda2 star, and this is a psi2 psi1. Now already they have defined this operator A is a Hermitian operator. So what is the meaning of this? It is having real eigenvalues. If it is having a real eigenvalue, I think this lambda2 star, we can write it as simply lambda2. Fine. Now carefully observe. See this left hand side and see this left hand side. Since A dagger equal to A, these two left hand sides are equal. So then what we can say? We can say from this, let it be 2. So from 1 and 2, we can say that right hand sides equal. That means lambda2 psi2 psi1 minus lambda1 psi2 psi1 equal to 0. because these two are equal. So we can bring one term this side, and here finally we got this is nothing but lambda 2 minus lambda 1 into the inner product psi 2 psi 1 equal to 0. So here we may have two options. Either this term is a 0 or this term is a 0. What is the meaning of this term is 0? Then lambda 2 minus lambda 1 equal to 0 means lambda 1 equal to lambda 2, which are degenerate eigenvalues. But clearly mentioned, these are different eigenvalues here, distinct eigenvalues. So that's why since lambda 1 is not equal to lambda 2, so here I am writing since lambda 1 is not equal to lambda 2, so we can say that a second term must be 0. So what is the meaning of inner product of two vectors equal to 0? That means both are orthogonal to each other. So if there is two eigenvectors of a Hermitian operator corresponding to two distinct eigenvalues are always orthogonal, right? So right, now this is our next question, and here they are asking to show that the eigenvalues of projection operator are either 0 or real, either 0 or 1. Okay, so now here I'm defining this projection operator. So this is the projection operator. So what is this projection operator? We have already defined projection operator p square equal to p, and two properties it satisfies. Of course, it's a Hermitian. P dagger is equal to p. So definitely eigenvalues are real. Okay. So now I'm taking this eigenvalue equation corresponding to projection operator p psi equal to lambda psi. This is the eigenvalue equation corresponding to projection operator. Let us suppose. Now I am taking a p square psi. What is the meaning of p square psi? Just operate two times on psi. One time operate lambda, one more time operate lambda square and psi. But we know one thing, this p square equal to p. That's why I can write this as p psi equal to lambda square psi. So here we have two equations. Let us say this is equation 1 and let us say equation 2. So from these two, the left hand sides are equal, and we can say this right hand sides also equal. So what is the meaning of this? So lambda psi equal to lambda square psi. Just bring one side, that means lambda square minus lambda into psi equal to 0. Since psi is not a null vector, okay, so then we can take a lambda square minus lambda equal to 0. This is a lambda into lambda minus 1 equal to 0. So finally here we got lambda equal to 0 and lambda equal to 1. That's it. Okay. So here this is our next question, and they are asking positive operator is necessarily Hermitian. So that means they are asking to show that any arbitrary operator is given, it can be written as a linear combination of a Hermitian and anti-Hermitian. So where we will use this in our physics, in quantum physics. So for example, if you have linear harmonic oscillator, in the linear harmonic oscillator, we will define creation operator and annihilation operator. So creation operator is nothing but 1 over under root 2h cross m omega x minus ipx cap. So if you see, you can bring this constant, okay, this is nothing but some c1 x cap plus a c2 ipx. Or you can write minus also, it's not a problem. Minute minus. And this is a dagger. If you take a, which is a 1 over under root 2h cross m omega x cap plus ipx cap. So here you have written again a linear combination of x and px. See this x and px are Hermitian operator. And one more example we can give, this angular momentum algebra. So in case of angular momentum algebra, we have this ladder operators which is L plus. L plus is equal to some arbitrary operator. This while we are constructing this L plus, we will write it as Lx plus iota Ly, where Lx and Ly are Hermitian operators, and similarly this L minus is also Lx minus iota Ly. So finally, if an arbitrary operator is there, we can write it as a linear combination of two Hermitian operators. See, this is the Hermitian and this is the Hermitian. So similarly, here they are asking any arbitrary operator A can be written as the linear combination of two Hermitian operators B and C. This is what we have to show. Okay, let us proceed. Now here, just I am assuming, just consider A, that's it. This is the A cap. I think I can write it as A cap by 2 plus A cap by 2. Yeah, no issue. And after that, plus I am taking A dagger by 2 and minus A dagger by 2. Fine. So, okay. Now I'm just rearranging this. How I am rearranging? A plus A dagger by 2, one term, and after that plus A minus A dagger by 2, another term. Okay. Next, what I'm doing is, here we want to get this iota. That's why I'm multiplying here iota and one more iota here. There's no issue. So finally, here I got this format. If you see carefully, Hermitian operator, iota, Hermitian operator. See, Hermitian operator, iota, Hermitian operator. Either plus or minus, it's a linear combination. So I can define this as a B cap and I will define this as a C cap. Now I have to show that this B and C are Hermitian operators. Okay, let us check. So finally, I'm taking a B with a dagger. So B is A plus A dagger by 2 whole dagger. So this is nothing but A dagger plus A dagger whole dagger is A by 2, which is B cap again. So B is a Hermitian. Next, if I take C and apply dagger, this is my C, A minus A dagger by 2 iota whole dagger. So now this A dagger minus as it is, A dagger whole dagger is A by, this is a 2 iota, that's why we can write it as minus 2 iota. Iota dagger is minus iota. So now just take minus common and this minus gets cancelled, and this is A minus A dagger over 2 iota, which is nothing but a C cap. So finally we can say this B dagger equal to B and a C dagger equal to C. So both are Hermitian. So the final conclusion, so any arbitrary operator, we have any arbitrary operator A cap can be written as the linear combination of two Hermitian operators, that is a B cap plus iota a C cap. In this format we can write. So these are the best examples in quantum mechanics in a linear harmonic oscillator and angular momentum algebra. If you have any doubt, so please contact. So here this is our next question, and they are asking for any operator A, show that A dagger A is a positive. So what is the meaning of one operator is a positive? So you have to find the expectation value of that operator and show that it is a positive value. That means greater than or equal to 0. Okay. So right. Now I'm taking the expectation value of this operator A dagger A. So here the given operator is A dagger into A. I'm finding its expectation value or average value A dagger A. So how to find this? This is simply some arbitrary state psi and A dagger and A psi. Earlier I have given some Dirac notations in earlier problems. Whenever an operator inside the ket vector, it will be out as it is, And whenever an operator in a bra vector, this can be written as a psi, bra psi, and here it is a dagger. You will get the Hermitian conjugate out. So by using that technique, here I have a dagger, so I can write it inside, and here it is a, so I can write here inside the ket vector. So this means we can write this as a psi, but it is a bra vector, and this is a psi ket vector. And you know one more thing, whenever you have something, a bra and a ket, if both are same, we can write this as a simply psi star psi, which is a mod psi square. So similarly, here we have something and here something. This is in the ket and this is in the bra vector. So both are complex conjugates of each other, and we can write this as a psi mod square. So once you find that mod square, this is always a positive. That means never be negative, either positive or 0. So it should be greater than or equal to 0, right? And this is our next question. And they have given psi, which is a linear combination of two computational bases. And they are asking to find the tensor product of psi, I mean 2 times, and this is a 3 times tensor product. Okay. So here we have a computational basis, 0 and 1, psi equal to 1 over root 2, so 0 plus 1. And we can write this in the matrix form, 1 over root 2, just take the coefficients 1, 1. So this is our psi. Now first let me find, so what is this tensor product 2 times psi. This is nothing but ket psi, tensor psi. Okay, fine. So just write this psi 1 by root 2 whole square, so 2 times, and the first vector is 1, 1, and the tensor product 1, 1. So what you have to do is just take this second vector and multiply with each and every element of the first vector. So this is 1 by 2. Just take this and multiply with this. That means 1, 1, 1. This 1 into 1, 1, 1, 1. That's it. So this is the psi tensor 2 times. And you know, if that means here we can write this as a linear combination of 2 qubit basis states, which is psi tensor product 2 times equal to 1 by 2. This is nothing but 0, 0, 0, 1, 1, 0 plus 1, 1. In a decimal notation, we can write this as 1 by root 2, sorry, 1 by 2. And this is a ket 0, 1, and 2, and 3. That's it. Now he is asking the next one, that means 3 times a tensor product. So what is this 3 times tensor product? Already we got 2 times this tensor product, so I can write this as 2 times a tensor psi. And this one already we got 1 by 2, 1, 1, 1, 1, and again tensor this 1, 1. Now you just, of course, here psi means 1 by root 2. That is, finally we can write it as 1 by root 2 whole cube. Okay. And now just take this and multiply with each and every element. Okay. So then you will get 1, 1, 1, 1. I think 8 times you will get. Yes. So we can write this as a linear combination of 3 qubit bases, 1 by root 2 whole cube. So this is nothing but, so 1 by root 2 whole cube, just I am writing a 3 qubits basis states, ket 0, 0 to 7, 1, 2, decimal notation I am using here, 4, 5, and 6, 7. Right, that's it. So let us go to the next question. And here they are asking the tensor product of Pauli operators x, z, and I, x, and x and I. So earlier we find the tensor product of state vectors, and here we are finding the tensor product of operators. Okay, so the first one, they are asking tensor product of x, z. Okay, so our Pauli matrix x is a 0, 1, 1, 0, and this is a tensor with a z. So very simple, you have to take this matrix and multiply with each and every element of this first matrix. But here zeros are there, that's why no need to multiply, leave it. Wherever 1 is there, just take this z and substitute there. That means nothing but 0, 1, z, and this is the z, and this is also 0. But remember, it is a 2 by 2 matrix. So if you want to write this general notation, this is a 0, 0, 0, 0, and this is a z, 1, 0, 0, minus 1, and again 1, 0, 0, minus 1, and this is 0, 0, 0. But better to remember this one. This is the x tensor z. And the second one. And the second one is I, identity tensor with the x. So identity matrix 1, 0, 0, 1, and a tensor product with x. Just take this and multiply with each and every element of the first one. So then this is nothing but x, 0, 0, x. Remember, it's a 4 by 4 matrix because all are here the order 2, right? And the next one, third one, that is x tensor I, identity. So this time we have x here, 0, 1, 1, 0, tensor product with I. Now just take this I and multiply with each and every element of the first matrix, which is a 0, identity, identity, and 0. Remember, again, this is a 4 by 4 matrix. All these are 2 by 2 matrices. That's it. But remember, this tensor product is not commutative. That means I tensor x is definitely not here, not equal to x tensor I. It's not satisfying any commutative property. So let us go to the next question. And here they are asking to show that some rules of this tensor product. The first one, A tensor B conjugate equal to A conjugate tensor product with the B conjugate. And individual tensor product of conjugates equal to combined conjugate of tensor product. Let us see. So now for this, I am assuming A is a matrix. Let us suppose 2 by 2 order. So that is A11, A12, and this is A21, A22. Now first let me find this tensor product A tensor B, which is nothing but A11. I told you already. So we have to multiply this B with each and every element of the A. A11B, A12B, so better to write a little bit with a little bit space, A12B, and this is A21B, and this is A22B. Fine. Now I'm going to apply conjugate to this. A tensor B, just a complex conjugate, nothing else. It's just complex conjugate, no transpose. You just apply each and every element a complex conjugate. That is A11 star, B star, and A12 star, B star, and each and every element please take a complex conjugate. Now again I can write this as a tensor product, because here B star, B star, B star, every element of this matrix is multiplied with the B star. So that's why again I'm using that technique. A11 star, A12 star, and this is A21 star, and this is A222 star. Tensor product with B star. So no doubt, and this is nothing but our matrix A star, and this is a tensor B star. So finally, we can say that uh, A tensor B whole conjugate equal to A conjugate tensor product with B conjugate. So this is the rule number 1. Next, second one. Second one, he's asking the transpose. So combined transpose is equal to individual transports and tensor product. Let us take again, we have already this A tensor B already we have. Let me take that one more time. A11B, A12B, and this is A21B and A22B. So for this I am taking the transpose, whole transpose I am taking. This is whenever you are taking the transpose, you have to write rows as columns or columns as or columns as rows. So this is a A11 and I am taking a B transpose because I don't know what is the B, just write a B transpose. And here you will get A21 because I have written this row as a column and this B transpose. And this is A12 B transpose and this is A22 B transpose. Now again what happened, each and every element is multiplied with the B transpose. So again I can write this as the square matrix, the tensor product of B transpose. So which is nothing but A11, A21, A12 and A22. This is nothing but A transpose, the tensor B transpose. So finally, A tensor B whole transpose equal to A transpose, a tensor product B transpose. And the third one is combining these two properties. Third one. So third one, here he is asking this A tensor B whole dagger. So what is this dagger? Transpose of complex conjugate. A dagger is nothing but, this dagger is nothing but transpose of complex conjugate. So take the complex conjugate and after that apply transpose. There is no space, that's why I'm writing here. So this is by applying this first property, that is A tensor B whole conjugate is equal to A conjugate tensor B conjugate. I'm applying that property, A conjugate tensor B conjugate, and after that the transpose. Now this is a something, tensor something whole transpose is nothing but the tensor product of individual transpose. So which is nothing but A star whole transpose tensor B star whole transpose. Now again I am using the definition of a dagger, so which is a transpose of complex conjugate, which is nothing but A dagger, and this is nothing but B dagger. So finally we can say A tensor B whole dagger equal to A dagger tensor B dagger. That's it. So if any doubt, please contact. So let us go to the next question. So here they are asking to show that tensor product of two unitary operators is also unitary. Okay, so first let us define unitary operators. Now let u1 and u2 are any two unitary operators. Any two unitary operators. Okay, so what is the meaning of that unitary operator? That means it satisfies one property, that is u1 dagger equal to u1 dagger u1 equal to I. And similarly, this u2 also satisfies u2 dagger u equal to u2, and it's a dagger, the product is always equal to identity. Okay, fine. Now here we have to take the tensor product of these two unitary operators. So I am taking u1 tensor u2. So I have to check whether it is unitary or not. If you want to check unitary or not, that means we have to take its corresponding dagger and multiply both. If you get I, so it is unitary, otherwise not unitary. So that's why what I'm doing is I'm taking its dagger, corresponding dagger, that is a u1 tensor u2 whole dagger. So I have to multiply these two. Okay, but from the earlier property, this one, a tensor b whole dagger equal to a dagger tensor b dagger. So I can write this as u1 dagger tensor u2 dagger. That's nice. Now I have to multiply these two, this and this. Now u1 dagger u2, sorry, u1 tensor u2, and this is u1 tensor u2 whole dagger. We have already written this as u1 dagger tensor u2 dagger by using the property. So this is u1 tensor u2. Now here one important property you must remember for the upcoming lectures of circuit analysis also. What is that? Whenever you have a tensor b into c tensor d, for example, then always remember there is this is very important rule. You just take the first terms and multiply. This is ordinary multiplication, not a tensor multiplication. This A and C, if these are operators, this is just ordinary multiplication or the scalar multiplication, A, C. And take these two, that is second B and D, and multiply, and in between tensor. So first and first, second and second. If three are there, first, like that, second, you have to multiply like that. Okay, I think, oh, it's okay. Now whenever here you have two terms, A tensor B, C tensor D, just take here first and here first, and just take here second and second. And this is the ordinary product, and this is also ordinary scalar product, and combined this is the tensor product. So please don't forget this, it is very crucial. So by using that rule, I'm taking this first and first, that is a u1 dagger tensor. This is a u2 and u2 dagger. Okay, so which is nothing but this, you know what is this, I identity and a tensor identity. Again, this is nothing but identity. So that's it. We can say that the product of two unitary operators is also unitary. Right? Next one. Show that the tensor product of two Hermitian operators is also Hermitian. Okay. So for this, let me define Hermitian operators, two Hermitian operators. Let A1 and A2 are any two Hermitian operators, or you can take B also, it's okay, anything you can take. A and B are Hermitian operators. Hermitian operators. So what is the meaning of a Hermitian operators? Means this is A dagger equal to A, and similarly B dagger equal to B. Now we have to check the tensor product of these two Hermitian operators is also Hermitian. Okay, so let me define the tensor product of these two, that is A tensor B. Cool. Now I have to check its hermicity. So that's why I'm taking its Hermitian conjugate, A tensor B whole dagger. Now I'm applying this property again. So A tensor B dagger equal to A dagger tensor B dagger. So this can be written as A dagger tensor product B dagger. Fine. So now I'm going to, okay, so fine. Now I'm going to check this hermicity. A tensor B whole dagger equal to, by using the property, that is A dagger tensor B dagger. But we know A and B are already Hermitian. That's why A dagger equal to A and B dagger equal to B. So finally what you get, something dagger is equal to something. So which is nothing but this tensor product of A and B is also Hermitian. That means A tensor B is Hermitian. That's it. So if you have any doubt, so please contact. Thank you.